Hello, Bemidji and other science learners from the region who are interested in the Science Center and the going-ons around here. Today we're going to be talking about soil, the structure of soil, how we classify soil, and how it is that we identify it. First of all, I just wanted to say a big shout out to the Beltrami Electric Co-op Roundup program for underwriting these streaming sessions. We really appreciate that. And also I should give myself an introduction. My name is James Will. I just started working here about a month ago. And this is my first stream, so I'm really excited to talk to you guys about some soil today. So the first thing I think that I want to talk about is I just want to walk through the structure of soil. So the first thing to keep in mind when thinking about soil is capillary action and water, and how water stays in soil and where it goes. So, first of all, to give kind of like an intro on capillary action, I'll show you how some certain materials react to water. So, if I take this piece of plastic here and fold it up, and I dip it into this water here, what do you think will happen? I'll pull it out. Maybe got some drips of water still hanging onto it, but for the most part, it's looking like this thing is pretty much unchanged. Water is hanging onto it on the tips, and that's called a process of adhesion. The polarity, the polar nature, the sort of magnetism in a way of water molecules sticks to the other polar molecules in this. But since plastic is hydrophobic, it mostly just runs off. However, we can then take a look at, for example, like a sheet of paper. And so we can stick that in here. And we'll see, even though I'm just sticking this thing in a little bit, it's possible to see that it's gone up the paper. And that's a process called capillary action. And so that means all of the tiny little pores in this paper attract the water fits into them and moves up. It's the same thing that moves blood around your body, capillaries. And then finally, if we have something like three-dimensional, like a sponge, we can imagine how this can completely expand. So I just slightly dip this sponge in the water here.
And so this is the same action that like trees use to move water in them as well, correct?
Exactly. And we can see how much this sponge has expanded on the side in all dimensions. So the presence of water causes materials that are sponge-like to expand. So then how does this apply to soil? Well, actually, it's kind of the most important part of soil. So if we go here, we can look at sort of a diagram of the structure of soil. So we have our plant cover, our grass, the stuff that you walk around down and you can see. You have the organic layer, the O horizon it's called, and the horizons is just the special word we use for the different layers of soil. And I can show you a sample of what we find in the organic layer. So we see here, wetland organic soil, and it's really mostly partially decomposed, like leaf litter is what we would call it, plants, dead grass, things of that nature.
I know when I was working for the Forest Service, we'd call it the O horizon, but also the duff layer is sometimes what we would call it too.
Exactly, and that's the stuff that, with the filtration of water through it, will leach into deeper layers of soil and start to form our fertile layers of soil, which we use for growing or, living, anything like that, giving us oxygen, capturing carbon out of the atmosphere. All very important things. So the next thing then that we have is the topsoil. And this is the most important to human agricultural needs. That's what we use to grow our plants. It's what, during the Dust Bowl, blew off the Oklahoma farms and fields when things got too dry and drought came in. And I'll find an example of some topsoil here. So now we can see this soil from Buena Vista, if you've ever gone skiing out there. The soil is clay, it's full of clay, that's what gives it the gray nature. It's held together with organic material, and it's full of nutrients and toxins and organisms. Right now, there's not much alive in it because it's so dry and it's been in the basement for so long. But on the other hand, then we can move down to the next layer called the substratum. Now the substratum is not exactly very exciting. It's just the layer of soil where water leaches through. And it's the layer of soil which cleans our water. So when we dump water onto the ground or water leaches in from our wastewater treatment plant, it moves through the substratum and adheres all of the toxins or pathogens, which are like the organisms that can cause disease, and also nutrients leach into the soil. And that's what leaves us with clean drinking well water in the aquifers deep, deep in the ground. So then we can move on, and we can look at the subsoil. And so here's where I've actually prepared some samples, because what I wanted to talk about is to show that subsoil and all soils, even if they're in the same layer, are all built differently. Soils are like an organism in the sense that they have different classifications, they have different nutrient contents, they have sand, they have loam being like organic material, like the stuff that you might find at the bottom of a lake, they have clay. And so here we have 3 examples. So the first thing I can show you is some subsoil from a wetland near here. And so I have rehydrated this stuff, and I'll show you here. And I can kind of squish it around like putty. And this is actually just playing in the mud, how we identify it. So I can do a few things. First thing, once I have it rehydrated, is I can just see, does it stay together? And that's a huge thing. I can take it, I can put it in like a little ball like this, and I can squish it, and it stays together. This tells us it's not sand. Like this, which is sand, another type of subsoil, from the same layer of earth, yet completely different. When I try to squeeze this, it just falls apart. That indicates a lack of organic material, and it's an open aeration, lots of spaces in the soil, lots of pores that can contain air and water, but it doesn't hold itself together. As opposed to this one, which I can hold together and squish. And so since I know that this one isn't sand, the thing that I can move on to is I can put a small piece of it in my thumb here. I can take it, I can squeeze it forward like a ribbon. I'll use a bigger piece. Squeeze it forward, just let it edge forward. And you can see this ribbon is extending out quite far before it decides to break. Now, with that in mind, I can look at my handy chart here, which I'll let you look at for a moment. And what this chart tells me is that if I can make a ribbon which is greater than 5 centimeters long, then I can move on to doing some different tests to see what it could be then. So I've narrowed it down, and I know that this is a type of clay. That's what it tells me when I can make a long ribbon like that. And so then what I can do is I can break off a little piece like this. I can put it in my palm.
So what would it be if it wasn't a clay? What's the alternative if it's not sand but you can't make a ribbon?
It could be loam, sand, or clay. Those are the 3 main classes in a sense. And clay is stuff like this which will hold together. You can get it really wet and it becomes kind of smooth. This stuff has a little bit of grit in it, so that tells me it's a little sandy. And so what I would call this is I would call this just clay. I wouldn't call it a sandy clay. I wouldn't call it silty clay. Just clay. There's some sand in here. And it's just as easy as that. Whereas then, with this one, like I said, since it squishes and falls apart, and it can't hold a ball, we just know that's sand. Whereas this, right here, is a little bit more interesting. And so, I can rehydrate this a little bit.
Just
Get rid of that one. And I can try the same process for this one. I can take it, maybe a little bigger piece than this. I can put it, I can squish it out, just push it out. And this one forms a nice long ribbon too. However, this one's more brittle, it falls apart, unlike the clay. So we can call this more like a loam. Then, doing the same thing we did earlier with the clay, I'll take a little piece of it and put it in my hand. I'll hydrate it, I'll drown it, and then I'll rub this one around too. And this one, I can feel a little sand in it, it's a little gritty, it's quite smooth. And so then looking at my handy dandy chart there, nice, smooth, we've decided it's loam based on how long of a ribbon. What that chart tells me then is that it's a silty clay loam. And I'll show you on here the process of this. Can you see the whole thing?
Mm-hmm.
So first here, I hydrate it. I get it into like a nice putty. I follow down the flow chart and I see that it can make a ball and squeeze it without falling apart. So I can continue down the flow chart. Then I can form a ribbon by pushing it out. So I move down next, and then I decide how long of a ribbon was it. I figured that one was like about a 2.5 to 5 centimeter ribbon. So then I go down, and then I do the final step, which is taking that little bit and putting a lot of water on it, and just feeling its consistency, and that's how I end on silty clay loam. And this is a type of thing, knowing how to follow these types of flow charts is a very important and useful skill to learn if you want to be a biologist or learn any sort of ecological science. Following dichotomous keys and flow charts can help you identify soil, it can help you to identify animals, it can help you identify trees, it can help you identify weather types. This kind of classification and flow chart is one of the most important tools scientists have to keep track of information. So, another interesting thing then we can talk about now that we've looked at how distinct each one of these soils are, despite the fact that they all come from the same layer, we can think of ourselves, where did they come from? So this one, the one which corresponds with what we called clay, this comes from a wetland. And it makes sense, because clay can hold all that water in, it can keep it, and so the water stays clear toward the surface and creates a swamp. Next, we have Bemidji subsoil. And so the Bemidji subsoil, it's sandy. And this makes it clear why is it that we have all these conifers, these pine cone trees all over Bemidji? Well, because they love this kind of soil. Open, aerated, lots of water can flow through it. And that's why we have so many conifers up here. And then we can look at Buena Vista, which is just, maybe 10, 15 miles outside of Bemidji. And we can see that this is like silt. And so it's very fertile, very green, very good for growth. And what's so intriguing about all of this is that we have this vast soil variety in just a small little area. Soils can be completely different just going 10 miles. And soils are the origin of how ecosystems emerge. They are the base, they are the structure off which an ecosystem grows. So understanding it could be very helpful to you if you ever want to learn more about ecological history or ecology in general, or just any type of biology. So then finally we can get down to the last two things, parent material and hard bedrock. the parent material is the structure that's inorganic. It doesn't have life in it, but it mixes with organic material, and it forms soil. And then beneath that we have the hard bedrock, and that's the final thing. You want to try playing with some mud? You don't have to. If
We
you
are
want
open
to.
today. Like I said at the beginning of the show, we're open 9:30 to 5, Monday through Saturday, and then Sundays we're open 1 to 5. It is, of course, about 3:45 right now, so we are open. So might hear some folks moving around off camera here. Yeah, if you want to check some of that stuff out, go right ahead.
You wanna come
We're streaming
play
right
some
now.
soil?
We're live streaming right now.
It's fine if you want to come up here,
Or if it's fine if you don't want to come
but
up.
if you don't want
Is
to,
it just fake?
What?
no, this is real. We're streaming.
Yeah, we're live right now.
Cool.
But anyway.
And so that is kind of an introduction, if you will, to soil structure. And for me, it's something I really care about, and I hope that by talking about this a little bit, I can bring some knowledge about something that's really important to me to some other people. So with that, I think that we're going to end this stream, and I think